When even a Nobel Prize winner in physics doubts our current understanding of the universe, everyone knows that the astronomical hour has come. However, Adam Rees is not the only one at his wits' end. The James Webb Telescope is currently detecting more and more new structures in space that are in stark contradiction to conventional cosmology. But how can it be that the existence of galactic structures previously considered absolutely impossible is being confirmed? What do these puzzling findings mean for future research, and have our previous theories finally had their day? Many simple questions require tricky answers. While the question of how fast the universe is expanding may sound simple at first, it actually goes to the heart of a research mystery that has had experts racking their brains for many years. It is now considered certain that the universe has been continuously expanding since its birth around 13.8 billion years ago. As a result, galaxies are also moving away from each other at a speed that is proportional to the distance that separates them. In other words, if Galaxy A is twice as far away from Earth as Galaxy B, its distance from us is also growing twice as fast. The American researcher Edwin Hubble was one of the first to recognize this correlation. To calculate how fast two galaxies are moving away from each other, you need to know their distance on the one hand and a constant by which this distance is multiplied on the other. This is where the so-called Hubble constant comes into play, and this is where it gets extremely confusing. There has long been a major dispute among experts about how large this constant actually is. After all, previous measurements have produced completely contradictory values. In other words, the results we obtain depend on the measurement method used. One method is based on the cosmic microwave background radiation, an almost isotropic relic from the early days of the universe, which is regarded as outstanding evidence for the Big Bang theory. If we use the expansion rate of the universe from this method, we obtain a value of around 67 kilometers per second per megaparsec. To put this into perspective, 1 megaparsec corresponds to 3.26 million light-years, where 1 light-year corresponds to around 9.46 trillion kilometers. However, if we use so-called Cepheids to measure distances in space, or in other words, a certain type of star in which the fluctuations in brightness are strictly periodic, the expansion rate is suddenly 73 kilometers per second per megaparsec. The universe therefore appears to be expanding faster in our vicinity, up to a distance of around 3 billion light-years, than in its entirety, and this should not really be the case. This discrepancy between the different values is referred to as the Hubble tension, and so far no researcher has been able to explain this unexpected deviation. Some scientists had previously hoped that the mystery surrounding the expansion rate was due to a measurement error by the Hubble Space Telescope. Adam Rees also wanted to find out whether an error had crept into the Hubble datasets. The physicist from Johns Hopkins University in Baltimore was awarded the Nobel Prize in Physics together with other researchers in 2011. The experts had discovered that the expansion of the universe is accelerating, and his team used the James Webb Telescope to find out the reasons behind the Hubble expansion and uncover any Hubble measurement errors. But how do you actually determine the expansion of the cosmos in detail? The so-called cosmic distance ladder is used for this. Each stage of this ladder is based on the previous stage, so a potential measurement error runs through all stages. The Cepheids mentioned only prove to be reliable up to a certain point because as the distance increases, the light from the Cepheids mixes with the light from other stars, making them relatively difficult to see conveniently. However, Webb is 100 times more powerful than its predecessor, Hubble. It allows experts to look further and in more detail than ever before into the remote secrets of the universe. The new study published in the astrophysical journal Letters then painted a rather sobering picture. The JWST covers the entire area previously observed by Hubble and found no measurement errors. So, the problem of Hubble tension still remains, and Adam Rees has a very brief and yet profound explanation for it. It could be that we have simply misunderstood the universe. Furthermore, we must now find out whether we have overlooked something in our previous investigations and how we can connect the beginning of the cosmos with the present. This solution calls Einstein's theory of gravity into question. Of course, the researchers around Adam Rees are not the only ones working on the confusing Hubble tension. Some scientists from the universities of Bonn and St. Andrews have also approached this mystery and found a new possible explanation. In detail, our blue home planet is located in a bubble-shaped region of space in which there is relatively little matter. The density of matter is higher around the cosmic bubble, and gravitational forces emanate from the matter, pulling the galaxies in the bubble toward the edge. As a result, they are also moving away from us faster than would actually be expected. This is a perfectly plausible explanation, but one that leads straight to the next research dilemma because the standard model does not provide for such bubbles or underdensities. They should not actually exist at all. Instead, matter should be evenly distributed in space. At its core, the standard model is based on a theory by Albert Einstein on the nature of gravity. However, it's possible that gravitational forces behave differently in reality than Einstein predicted. The scientists, therefore, refer to a modified theory of gravity presented by the Israeli physicist Moti Milgram in the 1980s. However, the so-called modified Newtonian dynamics (MOND) has not yet achieved more than outsider status, even though it accurately predicts the existence of the corresponding bubbles. Assuming that gravity really does behave according to Milgram's ideas, all the discussions about Hubble tension would also be a thing of the past. In this context, there would actually only be one constant for the expansion of the universe, and the observed discrepancies would be due to irregularities in the distribution of matter. The future will have to show to what extent this new approach will be accepted and confirmed.
But a look into the cosmic past also shows how much still needs to be understood in the future. Sometimes a single value is enough to leave even the most experienced astronomers with open mouths. In detail, 14.32% bright and massive at that time. Where did the necessary matter come from? Detected with the help of Webb's near-infrared camera, NIRCam, the structure is also likely to have taken 100 million years to grow to its observed size. The bottom line is that the galactic infant contradicts practically all theoretical models and computer simulations for the very early cosmos. In fact, the galaxy is in the best of company. The 6 galaxies that the James Webb Telescope had already added to the star maps at the beginning of 2023 were also much more massive than they should actually be. Although the structures already existed when the universe itself was only 500 to 700 million years old, they were already reminiscent of today's Milky Way. However, as this is simply not possible according to conventional cosmology, the galaxy Jades, GSC 13-0, earned the nickname universe breakers among experts. Instead of the unexpected baby galaxies, the researchers saw impressive objects, all of which contained more than 10 billion solar masses of stars. One of them could even have a mass of over 100 billion solar masses. The question that now needs to be answered is how this was even possible, because even if only one of these galaxies is real, this would push our understanding of cosmology to its limits. To explain the presence of the structures, the density of matter in the early cosmos would have to have been up to 5 times greater than our model suggests. Alternatively, the galaxies could have grown in a way that is completely unknown to us. But what do discoveries of this kind mean in a larger context? Does the history of the early universe, and possibly the Big Bang Theory itself, need to be rewritten from scratch? Our current understanding of galaxy evolution is as follows. First, dark matter collapsed into giant clumps called halos. This happened within the first few hundred million years after the Big Bang. As a result, the gravity of the halos attracted normal matter, eventually forming stars and galaxies. However, this process took time. The matter would have slowly clumped together and only gradually produced larger and larger galaxies. Within this model, the galaxies discovered by Webb are therefore impossible, and in addition, our previous theories do not predict nearly as many dark matter halos in the early universe as would have been required for the formation of the large structures. Yet some experts are already finding it difficult to completely abandon the established research consensus of the past. This includes Julian Manos from the University of Texas at Austin. Perhaps we would be better advised to interpret the data provided by Webb with a certain degree of caution. He points to the following fact. If there really were 10 times more dark matter structures in the early cosmos than assumed, then there would also be 10 times more galaxies in the Webb images. However, the same would also apply to the Hubble data, but this is simply not the case. Manos and his team counted how many galaxies Hubble had seen over a wide range of brightness. The researchers then set about the task of inserting more dark matter halos into their model of the early universe. The problem is that the halos needed to match the Webb data throw Hubble's information into chaos. But which telescope should we trust? There is no question that Webb is significantly more powerful than its predecessor, but it only began its scientific service in 2022. The Hubble telescope, on the other hand, has been gazing into the gigantic expanses of space for almost 35 years. According to Manos, quantity trumps quality at this point, and the Hubble data seems even more reliable at the moment. For this reason, we would currently be better off looking for other explanations for the inconsistencies. In the end, it is not only a matter of putting the pieces of the puzzle together, but of verifying the data from both telescopes. Overall, the current state of research in cosmology is a mix of excitement and uncertainty. The James Webb Telescope has certainly expanded our knowledge of the universe, revealing structures that challenge existing theories. However, the conflicting data from Webb and Hubble highlight the complexity of interpreting astronomical findings and suggest that our understanding of the cosmos may need to be re-examined. The future of cosmology will depend on how researchers reconcile these differences and integrate new discoveries into a cohesive framework. In the evolving field of cosmology, the quest to understand the universe's origins and its underlying principles has never been more dynamic or contentious. As astronomers like Adam Rees and their teams grapple with the complexities of Hubble tension and unexpected findings from the James Webb Telescope, they face the broader challenge of reconciling these discoveries with existing theories or developing new ones. One significant factor contributing to the ongoing debate is the nature and role of dark energy. This mysterious component, which is believed to be responsible for the accelerated expansion of the universe, remains one of the most profound enigmas in modern physics. Despite being a crucial element in cosmological models, dark energy has not been directly observed. Its effects are inferred from the rate of expansion of the universe, and discrepancies in measurements of this rate may hint at fundamental flaws or gaps in our understanding of dark energy. If new findings consistently indicate a faster rate of expansion than previously thought, it could suggest that dark energy behaves differently from current models or that alternative forms of energy might be influencing cosmic expansion. Another avenue of investigation involves the potential modifications to the Standard Model of particle physics. The Standard Model, which describes the fundamental particles and forces of the universe, has successfully predicted a wide range of phenomena. However, its limitations become apparent when faced with observations that contradict predictions. For instance, the discovery of unusually massive galaxies in the early universe challenges the model's assumptions about the formation and evolution of cosmic structures. These anomalies could suggest the need for new physics beyond the Standard Model, such as additional dimensions or novel particles that have yet to be discovered. Furthermore, the role of massive black holes in galaxy formation and evolution is an area of active research. The presence of supermassive black holes at the centers of galaxies, including those in the early universe, raises questions about how such objects could form and grow so quickly. The current theory posits that black holes could grow by accreting surrounding matter, but this process might need to be revised to account for the rapid growth observed. Researchers are exploring various scenarios, including the possibility that primordial black holes, formed in the early universe through different mechanisms, could have played a role in seeding the growth of supermassive black holes. The analysis of ancient cosmic structures also necessitates a re-evaluation of the theory of cosmic inflation. Inflation theory proposes a period of rapid expansion shortly after the Big Bang, which explains the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. However, if new observations reveal discrepancies with predicted inflationary patterns, scientists may need to reconsider the dynamics of inflation or propose alternative mechanisms for the early universe's rapid expansion. The interplay between observational astronomy and theoretical models is crucial in addressing these challenges. The use of next-generation telescopes and space missions will continue to play a pivotal role in refining our understanding. For example, upcoming observatories such as the extremely large telescope, YELTI, and the Square Kilometre Array, SK, are expected to provide unprecedented data on cosmic phenomena. These tools will offer deeper insights into the structure and evolution of the universe, potentially shedding light on discrepancies and confirming or refuting current theories. Moreover, The integration of data from various sources and missions is essential for developing a comprehensive picture of the cosmos. Collaborations between different research teams and observatories are increasingly important, as they allow for cross-validation of results and the synthesis of diverse datasets. International efforts, such as those coordinated by the Event Horizon Telescope (EHT) collaboration, which successfully imaged the event horizon of a black hole, exemplify the power of collective scientific endeavor in advancing our understanding. As cosmology continues to evolve, it is also important to consider the philosophical implications of new discoveries. The potential for revising fundamental theories or even overturning long-held beliefs raises questions about the nature of scientific progress and the limits of human knowledge. While scientific inquiry is driven by empirical evidence and skepticism, it is also guided by the pursuit of deeper truths about the universe. In conclusion, the field of cosmology is at a crossroads, with new data challenging existing theories and prompting a re-examination of fundamental concepts. The discoveries made by the James Webb Telescope and other observational tools are reshaping our understanding of the universe, revealing both exciting possibilities and significant uncertainties. As researchers continue to investigate these cosmic mysteries, the integration of new data with theoretical models will be crucial in advancing our knowledge and addressing the profound questions that lie at the heart of cosmology.